let's attempt to evaluate the indefinite integral of 1 over the square root of 1 minus x squared dx. And you might be tempted to use something like substitution here, but you'll discover very quickly that it is not working out. You might say, okay, maybe I have this function, I just need its derivative, but the derivative isn't sitting out here someplace. So instead, we're going to use a different technique, and the technique we're going to use is called trig substitution. So still a form, we're going to be doing some substitutions, but we're going to use trig functions and trig identities to try to simplify this expression into something that we can take the antiderivative of. And in this case, we're going to leverage the idea that sine squared theta plus cosine squared theta is equal to 1. This comes straight out of the unit circle definition of trig functions. Or if you subtract sine squared theta from both sides, you get cosine squared theta is equal to 1 minus sine squared theta. And so you might immediately see a pattern. We have a 1 minus an x squared. We have 1 minus sine squared theta. So if we set x to be equal to sine of theta, x is equal to sine of theta, then 1 minus x squared would be equal to 1 minus sine squared theta. And then we can leverage this trig identity right over here and say, well, that would be equal to cosine squared theta, which is pretty convenient because it would be sitting right here under a radical so that we could then take the principal root of that. So let's make that substitution. X is equal to sine of theta. Later on, we're going to have to undo the substitution. So let's solve for theta in terms of x. So let's say, if we take the inverse sine of both sides, we get theta is equal to arc sine, or inverse sine, arc sine of x. And then this automatically limits the range of thetas that we might have. So you might say, wait, aren't we limiting our x's? Because sine of theta can only produce an x between 1 and -1. But that's really just our domain here. In fact, we can't even equal 1 or -1. Then we'd get 1 over 0. But in order for this principal root to make any sense, x has to be, so already over here, our domain is being restricted to x has to be less than 1 and greater than -1 in order for this stuff down here to make any sense. In order to evaluate the radical, we could have this greater than or equal or less than or equal in order for the radical to be evaluated. But then if x were equaling 1 or -1, the denominator right over here would be 0, square root of 0 is 0, and you would have 1 over 0. So the domain for this entire expression right over here is this right over here. So it's completely fine. We're actually not limiting the domain by saying x is equal to sine of theta. Now, when we write it this way, as theta is equal to arc sine of x, this does give us a sense of the range that theta might take on. So arc sine, as it's typically defined, will produce a theta. It will produce a theta that is less than or equal to positive pi over 2 and greater than or equal to negative pi over 2. Just as a little bit of a review of the unit circle and to visualize what the arc sine function is doing, that's our y-axis. That is our x-axis. If you imagine this is the unit circle, this is the unit circle, this is the unit circle right over there. We're giving a value between 1 and -1. So we're giving a value between 1 and -1 into the arc sine function. And then the theta it gives, it could give a theta that responds to something out here, but so it's an actual function, it'll only give you the theta. It'll only give you a theta, as it's traditionally defined, that's between pi over 2 and negative pi over 2, or between negative pi over 2 and pi over 2. So it'll only give you an angle that makes you sit in the first or the fourth quadrants, which will be useful later on because right over here for any of these thetas, if we're sitting in the first or fourth quadrant, our x-coordinate is always going to be positive. So for any of these thetas, that we hit, cosine of theta is going to be positive. Cosine of theta is going to be greater than or equal to 0 in any of these situations. It's going to be useful as we try to simplify this expression. So let's try to substitute back. And the only thing we have left to do, we already know that x is equal to sine theta. Theta is equal to arc sine of x. But we also have to figure out what dx is equal to. We also need to figure out what dx is equal to. We could say dx d theta is going to be equal to just derivative of this with respect to theta, which is just cosine theta. Or we could write that dx is equal to cosine theta d theta. Now we can substitute everything here in terms of, or replace everything that's in terms of x here, we can replace them in terms of theta. So our original expression becomes the antiderivative of And instead of writing 1 times dx in the numerator, I'll just write this, cosine theta d theta. So let me write this, cosine theta, I'll write the d theta right out here, cosine theta d theta. All of that's going to be over the square root of 1 minus x squared. We already know that 1 minus x squared is 1 minus sine squared theta, which is cosine squared theta, And I think you see where this is going. Now we have to be careful here. If I have the square root of x squared, this is equal to the absolute value of x. If x is positive, this is just going to be equal to the x. 3 squared, the principal root of that is just positive 3. If x is negative, if you have negative 3 squared, that goes to positive 9, you take the principal root, you get positive 3. So you're essentially taking the absolute value of x. Now, what's useful here, so based on that, we would say that the square root of cosine squared theta is equal to the absolute value of cosine theta. But lucky for us, we have already limited theta to values where cosine of theta is going to be non-negative. So this, because cosine of theta is greater than or equal to 0, this is going to be just equal to cosine theta. So then this whole thing simplifies to, this is equal to our blue cosine theta over our green cosine theta. This simplifies to the absolute value of cosine theta, which is just cosine theta, since cosine theta is positive, d theta. Cosine theta over cosine theta is 1. So our whole integral has simplified to the indefinite integral of d theta, which is equal to, or we could say it's of 1 d theta if we like, which is equal to theta plus c. And you can verify this. Take the derivative of this with respect to theta is 1, and this is just 0. So this makes sense. But we want our answer in terms of x. Now we just have to undo the substitution. We have theta is equal to arc sine of x. So this is going to be equal to arc sine of x plus c, just like that. And we are done. And by doing this problem, we've also helped figure out what the derivative of arc sine is, if you think about it that way. But we'll do more and more examples of these that get progressively more complicated. But this is a major pattern to see. When you see 1 minus x squared, or as we'll see if you see a squared minus x squared, where a is some constant, that's a pretty good sign that you'd want to substitute with x is equal to, let's say, sine of theta.